How do we describe how position changed in time? Okay, you started out class by picking up a lab sheet and the non-textbook reading for the night. Okay, we talked about a few things before you started the lab, and then hopefully you collected some data. I realize, especially for first period, there were a lot of obstacles to overcome collecting your data, but for the most part, we got some. Okay, and once you had your data, your position from the readings was, in reality, your. So from that, you calculated the distance traveled for each data point. And you got more or less towards writing proportionalities. Now, I realize not everyone finished this, and I'm sorry I had to interrupt some of the classes, but we really kind of had to get through the next bit, which was the important part. Okay, so most classes at least noticed that for distance, it increased roughly linearly with time, whether or not there was an initial offset, because we made some assumptions about where the 0 point was. So that relationship is for distance and time, and it's what we call speed in daily life. And it is in physics too, as long as we're talking about our physics definition of the word distance. Okay, so from the proportionality that distance is proportional to time, we can get our average speed. Okay, so when I write that down at the bottom, I switch that proportionality to an equation. I have that distance, that's what the d is equal to the average speed. That's what the bar over the s means, it's average. All right, so average speed times the change in time. Now that's an equation, I can switch it around to solve it for the average speed. This is probably more how you're used to seeing it written. Distance over time. So, most of the time when we set our time scale, we're going to call our initial time 0. So my delta t, final minus initial, would just be the same as the final. So a lot of times, we'll drop the delta in front of a delta t. If you ever get confused by this, please come ask me, because it can get confusing. Alright, so when I write the average speed equation, the one on the bottom right there, average speed equals d over t, distance over time. That's how I'm going to write it. Okay, so the other data set. If you looked at the graph of displacement over time, which is what you got on the motion detector, some of you guys noticed it looked kind of like an absolute value function, with a little bit of a squiggle where the car was turning around. So maybe it had something to do with that. And in this case, the graph didn't give us a lot of insight. We're going to talk more about graphing motion next week. So, if the relationship between distance and time is speed, the relationship between displacement and time had to be called something else. In physics, we call it velocity. So, you might have seen this word before, okay? And you might have been told that speed is just the magnitude of velocity, where velocity is speed plus direction. That's kind of true, but it's not quite the whole story. So, velocity, here we're only talking about average velocity. That's all you could find today. We don't have the tools to do any sort of instantaneous velocity yet. And that's where we'll start seeing the distinction between speed and the magnitude of velocity, because sometimes there'll be a difference. Okay, so for today, don't worry about that. But the average velocity is your displacement, so your change in position over your change in time. For this one, you'll notice I've left the delta in front of the delta t, or as part of the delta t. This is because when you get to calculus, those deltas become something else, and we can go from taking the average velocity to instantaneous velocity, even when the motion's very complicated, more so than what we'll do in this class. Okay, so we had a short conversation, all right? When would the average velocity be the same as average speed? So if I go in one direction and I stop, my displacement is the same as my distance. Therefore, my delta x is the same as my distance, so average speed will give me the same value as average velocity. Okay, so when would my average velocity be the same as instantaneous velocity? This one's a little trickier. So if I am moving at a constant velocity, say 2 meters per second in some direction, all right, and I walk for 5 seconds, my displacement then would be 10 meters in whatever direction I was going. Okay, but if I take that, my displacement over time, 10 over 5, that gives me 2 meters per second in whatever direction I was going. Hey, so that in case my average velocity was the same as my instantaneous velocity at any point in that part of the motion. Your homework is to read Willing to be Disturbed, which is an article I handed out in class. This is what you picked up at the very beginning. I know that some of you are still getting used to how this class is set up and having to get used to watching the videos and the fact that sometimes we don't have the answers and sometimes I make you think about things that maybe you already knew a little bit about and I make you dig a little deeper. So please, as you're reading through this, think about how this applies to my physics class and maybe why I've set up some things the way I have. Okay, back to the physics stuff. Read OpenStax, section 2.3. This is the section on time, velocity, and speed. It should be pretty much what we talked about in class today. I left this one in here. If we didn't finish, I was just going to have you watch the video about speed and velocity, but we got there in all the classes. Don't forget your project is due on the 25th, and your mastery quizzes are still open. All right. Hopefully you had a chance to write about the difference between speed and velocity in your notebook. All right. Between the lab and the video lecture, I hope you got what you needed. If not, please do come see me or refer to the textbook. Stay dry. It's pretty rainy out there.